So what is a directed graph? A directed graph is a graph, so we still have vertices or nodes and edges between them. And now for every edge that I have to choose a direction. For loops, of course, it sort of doesn't matter which direction you choose, but for this edge, this is different from going down there. How does this relate to de Bruijn sequences that we were just talking about? Well, I can take this is an example of the de Bruijn graph. The vertices of the de Bruijn graph, so the vertices is going to be binary sequences of length n minus 1. So here is an example where n equals 3, so n minus 1 will be 2, so I'm going to put all binary sequences of length 2 into this graph. There, I've done it. These are my vertices. What are my edges? My edges in this graph, now keep in mind it's directed, so I have to tell you when you go from here to there. I go from here to here, okay, so from one node to another. If I can tack a number onto the end of this node, delete the first and end up there. So how could I do this? So I could think about a 0, okay? If I'm here, think about adding a 0 to the end of the node. Then delete the first. I would get 0, 0, which is the same thing. Okay, that was boring. What if I added a 1 to the end of this? Then I would cover this up, I would just have 0, 1, which is right here. Okay, and here, if I added a 1 to the end, I would cover this up, I'd get 1, 1, which is down here. But if I added a 0 to the end, I would get 1, 0, which is over here. And then going back, I could put a 1 here. And what's this? This is a 1. And I can go in the same way, and I can label all of my edges with a 0 or a 1. That edge labeling is kind of interesting, because I still haven't explained what this has to do with de Bruijn sequences. Let's take an Eulerian walk. So remember that for an Eulerian walk, we want to cross every edge exactly once. I'm going to start up here at this vertex, and I really want it to be a cycle. So I'm going to start up there, and I'm going to make a record of the edges that I cross, okay? So I'll start here, and I'm going to go first down here. So I'm going to start with a 1, okay? I'm just writing this down, but this is the first one I do. And then what am I going to do? Maybe I'll go over here next. Remember, Eulerian walks are easy to get. You just take a walk anywhere you want. Now, if I take this one, I'm never going to get this edge, right? Because once I leave, I can't come back. So I better take that loop now. So I'll take the loop now. So there's a 1. And then I'll exit out this way, 0. Okay, and now if I go up here, I'm already back and I can't finish. So I better go out with a 1 and then come back with a 0. And now I can go up here with a 0. And now I'm going to finish off with this little loop, 0. And remember, these are cyclically oriented, but you can see that, excuse me, this is the same the same de Bruijn sequence that we had before, but in fact, this is exactly a de Bruijn sequence. And this is a bijection between Eulerian walks on the de Bruijn graph and de Bruijn sequences. So this is kind of an amazing thing that we can get. And de Bruijn sequences are really interesting. We'll talk more in class about some applications of them. But for now, it gives us a nice introduction and motivation for directed graphs. And now I can know why do de Bruijn sequences exist? Well, because I can take an Eulerian walk on the de Bruijn graph. Why? Well, that's for you to figure out. But for now, let's talk about just some examples of directed graphs and things that we can do to them. So we need to put some definitions. Directed graphs are interesting. Here, the same graph with 2 different orientations. And let's think about some properties of this graph. So first of all, it's connected, right? But one thing that we notice is that they're connected means something different in a directed graph. So a graph, I'd say a digraph, a directed graph, is strongly connected if for every 2 vertices x and y, there exists a directed path from x to y. So let's look at these 2 examples and say which of these, if either, is directed. So what I want to do is think about every pair of vertices. Can I get from one to the other? So if we start, say, at this guy, can we get everywhere? Well, I can certainly get down here, and I can certainly get over here. Can I get here? Well, sure, I can go this way. So this guy, check. He can get everywhere. This vertex, you can just check. Again, I can go here, there, or all the way over here. So that one works. If we're here, we can get all the way to there, to here, and to there. If we're here, we are completely screwed. We can't get anywhere. So this is not strongly connected. So it's a connected graph, but it's not strongly connected. And then we can look at this guy. This one is, for the same reasons, not strongly connected. But if we flip some of these arrows, we can probably get it to be connected. But I wanted to use that one for a different definition. So that's one thing. The notion of what it means to be connected is subtly different for a directed graph. So here's another definition. So we're going to have, remember we talked about the degree of a vertex. Well, now we can talk about the degree in and the degree out. So the degree in is the number of edges coming in that go in to V. And the degree out is the number of edges that go out of V. So let's go ahead and mark up over here some of the degrees. Here, the D out is equal to 2, and the D in is equal to 1. And notice the total degree of this vertex is 3, which is, of course, the sum of these two. We're going to call a graph balanced. A directed graph is balanced if dn equals d out for all vertices v. So we can ask ourselves, does that happen? Well, here it's not going to happen. It's not going to happen when you have a vertex that has odd degree, because there's no way that you're going to have these two be equal and add up to an odd number, right? And that's an important thing, because remember when we were talking about Eulerian walks and we asked if they existed or not, we saw that an Eulerian walk exists in a graph, all of whose edges are even. It turns out that in a directed graph, we need the following generalization. For a directed graph, okay, an Eulerian walk exists if and only if the graph is balanced and strongly connected. So let's think about why that is for a second. And we'll do a proof only in one direction. So the proof, and we're going to suppose that an Eulerian walk exists. So suppose that an Eulerian walk exists. For balanced, how do we think about that? Well, the number of times you enter a vertex equals the number of times you exit the vertex. An entrance will add 1 to the degree in, and an exit will add 1 to the degree out. And this means that the total degree of every vertex, of course, is even. It's the number of times in plus the number of times out, which is twice the number of times in. And then strongly connected, of course, because we take every edge. So take each edge. That implies that you hit each vertex along the walk, so that gives you your walk from any one vertex to another. So Eulerian cycles in a directed graph, it's not enough for the vertices all to have even degree. They need to be more than that. They need to be balanced.